Okay, welcome everybody to our next session. This is technology for surface exploration, in which we'll be talking about what's needed for successful surface exploration away from Earth. Our supporting sponsors for this session are Aerojet Rocketdyne, Ball Aerospace, and Teledyne Brown Engineering. Thank you to each of you for supporting this session. So to get right into it, I'd like to introduce Jim Zakrashak, Chief of the Materials and Structures Division at the NASA Glenn Research Center. Jim, come on in, unmute and turn on your video, and we'll get going. There you are, Jim. Be sure to unmute. There you go.
Yep. Okay.
All right, over to you.
Okay, thanks, Jim. Appreciate that. Good afternoon, and thank you for joining us in this panel session on technologies for surface exploration. As a little introduction to this session, once again, we will be putting boots on the moon and eventually Mars, and we'll need to make sure that our explorers are equipped with highly reliable and durable equipment to make the most of the time on the surface. Question being is, what technologies are being developed now to assure mission success in the face of daunting challenges like temperature extremes, the abrasive dust and radiation and high vacuum, plus also questions about reliable communications on the surface and obtaining basic elements of survival like water, breathable air from the lunar resources. Big question is, how will we know that will work? So this group and session is here to discuss the technologies that we're working now that are needed to allow humans to safely live, work, and explore in this extreme environment. We will be having 4 panelists in this session, and I'm requesting that you hold all questions until after all 4 panelists have presented their material. Our first panelist is Ms. Joyce Dever. Ms. Dever serves as Deputy Chief of the Materials and Structures Division in the Research and Engineering Directorate at NASA Glenn Research Center. She has over 32 years of experience at NASA Glenn, where she initially conducted research investigating space and environmental effects on spacecraft materials. She currently co-leads 10 technical branches with over 200 researchers and engineers conducting work ranging from research on aerospace materials to design analysis and testing of flight hardware. Okay, so I give it over to Ms. Dever.
Okay, thank you, Jim, and good afternoon, everyone. Can I have my slides, please? Okay, perfect. The portion of my discussion today will be on reliability for surface exploration, and I will talk specifically about reliability challenges and technologies to overcome these challenges for mechanical systems, materials, and communication systems. So next slide, please. Okay, so when we think about surface exploration for the Moon and Mars, there are a number of key challenges for mechanisms, materials, and communications. So probably really the biggest one that we face, it affects a lot of things, is dust. It's a huge challenge. It can be a detriment to mechanical systems and really any exposed material or surface that is used in exploration. Extreme terrain creates a great deal of challenges for getting around on the lunar and Martian surface. Challenges include rocky obstacles, craters, steep slopes, and variable conditions of the regolith or soil. And these regolith conditions can also affect signal scatter for communication systems. So harsh environments, that's another significant limitation. It can cause limitations on the selection of materials and can degrade materials and mechanisms. And so in addition to dust, harsh environmental conditions include temperature extremes, radiation, and the environment or atmosphere or lack thereof, for example, vacuum and others. And then for communication systems, limited visibility to Earth can have some reliability challenges, such as creating disruptions in communications. And technologies such as communication relays and other things are necessary to overcome that challenge. So NASA Glenn is playing a number of roles addressing these reliability challenges, working together with our colleagues across the agency and our mission customers and partners. And in the following charts, I'm going to share some examples. Next slide, please. Okay, so let's start with taking a look at technologies for roving vehicles. Reliable rovers will be very important to us. They'll be our robotic scouts. They will carry humans between locations on the surface of where we are exploring. And NASA Glenn has some capabilities that are really important to reliability for rovers. So if you were with us last year at the Glenn Symposium, perhaps you got the full virtual tour of our slope lab or simulated lunar operations laboratory, which is shown in the image here on the left. And the slope lab can actually mimic the terrain of lunar or Martian conditions, and has instruments that can measure traction and reliability performance for rover systems. So recently, our slope lab was visited by the engineering model of NASA's Viper, or the Volatiles Investigating Polar Exploration Rover. And Viper is a mobile robot with a destination to go to the moon's south pole, where it will look for water ice and take samples. And the Viper unit was tested at Glenn as the Moon Gravity Representative Unit. And the information learned by our teams is helping to provide information for the flight version of Viper, which is planned to be delivered to the lunar surface in 2023. So on the right in this slide, the images here represent NASA Glenn work developing wheel and tire assemblies for the sample fetch rover for the Mars sample return mission. So our Mars spring tire effort brings together work in developing new shape memory alloy materials, tire designs that can take advantage of the properties of these alloys, and testing capabilities to evaluate the materials in the tires. So the shape memory alloy tires have benefits of being able to envelop obstacles without permanently deforming. They can enable faster travel, steeper climbing, and operation over a wide range of temperatures. So next slide, please. So also our future explorers will need to be able to make use of resources on the surface of the moon and Mars. And so they'll need to be able to excavate materials as part of this. And so this chart shows two examples of excavation technologies. The image on the left shows our Advanced Planetary Excavator, or APEX system. And our teams are using this system to look at designs for excavators and really kind of putting these designs to the test for various soil conditions over a wide range of possible soil conditions. And the system can measure fundamental forces to excavate these granular soils, and the information that they're gathering from those tests is going to help inform designs of these excavators, as well as operational guidance, so that excavation can be done in a reliable and power efficient way. So on the right is another tool that can be used by our explorers to help with excavation, and this is a compact shape memory alloy rock splitter, and it uses a shape memory alloy element which is heated and produces a shape change, and that shape change provides enough force to reliably break rocks. So our explorers might be able to use this for gathering rocky materials for scientific studies and other uses as they live and work on surfaces. So next slide, please. Okay, so going deeper into the mechanical systems, NASA Glenn is addressing reliable seals, bearings, and drive systems for harsh surface conditions. And the images on the left here show NASA Glenn docking seal technology that's currently being used on the International Space Station and its docking vehicles. And to expand this technology for use on lunar surfaces, our teams are developing methods and evaluating these seals for their performance upon exposure to simulated lunar dust. So dust is also a significant problem for rotating machinery and drive systems, where it can infiltrate and cause abrasion damage. And as shown in the upper right images here, one example is bearing denting. So NASA Glenn is assessing dust effects and exploring technologies for mitigating these effects for a wide range of mechanisms and materials for mechanisms. So in addition to dust issues, cold temperatures and vacuum can place limits on mechanisms. And for example, for permanently shadowed areas of the moon, mechanisms need to be able to operate reliably at temperatures that are as low as minus 240 degrees Celsius. And for this extreme application, conventional space actuators have to either be heated or use solid lubricants, which can limit their performance or life. So shown here on the lower right is a concept for a magnetically geared rotating actuator that our teams are developing that can avoid the use of heating or gear lubricants and provide reliable rotating parts for lunar operating conditions. Next slide, please. So yes, we will continue to talk about dust. Dust is really a problem for all materials and surfaces that are going to be used in our missions. And so we want to really be able to evaluate and develop materials and surfaces that have promising properties to be dust resistant or that can repel dust. So in the image on the left, we have our lunar dust adhesion system, which is a laboratory system that allows us to evaluate materials and surfaces for their potential to be dust resistant, and also take a look at some technologies to help us remove dust that does settle on these materials and surfaces. So in our laboratory experiments on Earth, we'll pave the way for evaluations in real lunar conditions. And so directing you to the middle panel, our NASA commercial lunar payload services will be delivering precursor missions to the lunar surface to help us check out some of our new technologies. And these will include some opportunities to take a look at dust resistance of materials. So one example of this is a patch plate of dust mitigation materials, and that will be included on the regolith adherence characterization experiment for one of the CLIPS missions. So on the right-hand side, we'll talk about active dust, actively repelling dust, because it's not going to be possible to develop everything that we need with materials that are naturally or created to be dust repellent. We're going to have to do some active methods to remove or repel dust. And so NASA's Low Dust Project is looking at some of these technologies. And as part of this project, NASA Glenn is developing an electrostatic attraction system that's going to repel dust away from sensitive areas and take them away from those areas so that we can have more reliable operation. Okay, next slide, please. So another important consideration for reliable operation on the Moon and Mars deals with communication systems. And so this illustration shows how elements for lunar surface missions would be able to communicate with each other, with the orbiting gateway, with communication relays, and directly with Earth. So while this illustration depicts approaches that could use current technology, as our missions evolve and our capabilities increase, we want to make sure we have new communication technologies to help reliability for those operations for the future. So a few examples of NASA Glenn technology for reliable communications technology include orbital relays, delay-tolerant networking, and work on cognitive communication systems. So cognitive communication systems will have more autonomy and less human involvement in decision-making, and they will be able to sense hazards or interference that's encountered and be able to make operational changes to overcome those challenges and help sustain reliable communication. So to advance communication technology for the future, one of the tools that NASA Glenn has recently established is a new test bed for communications, and it's referred to as MATRIX, or Multiple Asset Test Bed for Research in Innovative Communication Systems. And this test bed will be able to explore a wide range of possible architectures and operational situations for future surface missions. So my final slide, just to wrap up. Thank you. Okay, just to wrap up, our future explorers will need reliable systems for surface exploration, and NASA Glenn, along with our colleagues and partners, is playing a number of roles to make that possible. Thank you for your attention.
Thank you, Joyce. Appreciate that presentation. Thank you very much. Our second panelist is Dr. Jonathan Ransom. Dr. Ransom is the Research Directorate Deputy Director for Structures and Materials at NASA Langley Research Center. He has over 38 years of experience at NASA Langley. He leads all Langley structures and materials research, where the mission is to innovate new materials, structural concepts that enable future aviation and space exploration, and to develop the foundational technologies essential for manufacturing, design, validation, and sustainment of aerospace vehicles and structural systems. So I hand it over to you, Jonathan.
Thanks, John. Greatly appreciate it. I'd like the first slide, please. So I believe the previous speaker did an excellent job in highlighting the challenges as it relates to surface exploration. I'll spend just a little bit of time talking about some of the the technologies that we're developing at Langley that allow us to work, live, and explore on the lunar surface. So the 4 areas that I'll touch on, and certainly our technologies extend past those 4 areas, but I'll just touch on with a little level of detail: radiation protection, regolith-derived materials. I'll talk a little bit about XEMU, the Exploration Extravehicular Mobility Unit, although I know another panelist will talk in detail about that, but I'll talk about Langley's contributions in that area, as well as the lightweight surface manipulator system. So the next slide really touches on what we see as the major challenges as it relates to radiation protection and shielding. Primarily, we know that radiation is a tall tent pole as it relates to long duration space exploration. And there are 2 different environments that we are concerned with as it relates to space radiation: the galactic cosmic rays, as well as solar particle events. Each of these have their own characteristics that provide challenges for our ability to protect our astronauts and electronics. For GCRs, or galactic cosmic rays, these particles are energized ions that span the periodic table. And they're neutrons that are produced in the lunar regolith that we have to be concerned with. They're always present, but they vary with the solar cycle. They're small in daily exposure. However, they still increase the astronaut health risk for long duration missions. They're difficult to shield because of their deeply penetrated particles. One point to be made is, as it relates to galactic cosmic rays, as well as solar particle events, is that hydrogen-rich materials provide a better protection as opposed to aluminum or aluminum alloys. For SPEs, or solar particle events, these are low to medium energy particles. Large SPE are rare and short-lived. However, they occur at about 11-year solar cycle. And the last more significant SPE event was in 1972, which happened to fall between 2 Apollo missions. So we have to plan for the unplanned and provide for technologies that help shield our astronauts from such deleterious events. So we can effectively shield SPEs, but we need to take advantage of optimization so that we can reduce the parasitic mass. We don't want to take more with us than we need to take, and we want to use that which we take. We can also provide for unshielded exposure, or at least allow for unshielded exposure, but that could result in acute radiation syndrome. It could also impact the central nervous system, as well as provide for heart problems. With regards to the shielding technology, again, we want to take advantage of those hydrogen-rich structural materials. We want to integrate those in the design and provide for vehicle optimization to reduce those thinly shielded regions. In addition, we can provide for utilization of regolith to create a heavily shielded habitat. Of course, we want to be able to protect our astronauts as they live, and providing for a mechanism through the use of regolith is something that I'll speak to in subsequent charts. We also have fixed location or reconfigurable SPE shelters, as well as wearable SPE protection and blankets. On the next slide, we highlight the technologies that are necessary for us to, again, protect for astronauts in the event of exposure, and be able to assess exposure, provide for risk modeling and countermeasures. With regards to the assessment tools, we need to be able to provide for those tools that impact the vehicle design. We need to do so in an efficient manner such that we can bring these assessments early in the design process so that they can impact the subsequent design, such that we don't add that parasitic mass. So we want to be able to optimize the vehicle for GCR. We want to be able to utilize storm shelters and wearable protection, and also consider the mission duration and provide for such information as part of the EVA planning. With regards to the tools, we want to be able to model the space environment. We want to be able to model the vehicle via computer-aided design models, as well as include the onboard mass associated with those models, as well as modeling the humans via phantom modeling, as well as human risk models. And we use all of that as input to our space radiation transport codes, which have to be highly effective and highly efficient in order to be used early in the design. One mechanism for allowing for that or accomplishing that is via the development of the online tool for assessment of radiation in space, or called Alteris. This is a tool set that is somewhat user-friendly, is very efficient, and allows for the non-radiation subject matter expert to make assessments early in the design process. Uncertainties is also a key area as it relates to crew risk estimation. The uncertainties are due to the lack of experimental data associated with the space environment and its impact on humans. Often extrapolations have to be made based upon other radiation events, such as the atomic bomb survivors, or based on tests that have been done to animals. And so that creates some uncertainty associated with the assessments that have to be accounted for, and also and often done so in an unconservative manner, adding mass. We're also looking at the biological countermeasures, which are also key to being able to mitigate the impact of radiation on our astronauts. The chief scientists here at Langley often ask, how can we solve the radiation problem? And I believe it's the combination of all these things: vehicle optimization, the independent wearable type devices or shelters, as well as biological countermeasures. In the next slide, I'll talk a little bit more about the regolith-derived materials. We want to be able to use the surface when we get there. We don't want to carry everything with us. We want to, again, minimize the weight. And so we're doing research here at NASA Langley that's looking at these regolith-derived materials, looking at polymers for the most part, and looking at the consolidation of said particles into regolith simulant. And we are finding excellent consolidation, up to 80%, and the ability to shield against both SPEs and GCR. We're looking at small scale at this present time, but looking at scaling that up to something that would be more usable for shielding a habitat, for example, using regolith. The next chart highlights some of the information that just indicates the effectiveness of said regolith-derived materials, with on the left-hand side of the chart, experimental data being used to support the statement that we have determined that the regolith polymer materials do an effective job in fragmenting GCR ions. On the right of the chart, we see the neutron dose rate as a function of the aero density, which indicates that the regolith polymer materials do an effective job shielding against neutrons as well. The next chart just provides a summary of what I've just told you. That is that we're doing work with regards to the next chart, please. The regolith, with regards to regolith and derived materials from regolith for lunar surface construction. Regolith, as we know, is an abundant resource on the lunar surface, and we're looking at different consolidation mechanisms for that regolith, whether it be centering or binding with polymers. And we've shown the effective use of such consolidation for shielding against neutrons, galactic cosmic radiation, as well as solar particle events. And we're finding that consolidated regolith is superior for construction as compared to loose regolith. So we're using those technologies to then help assess how we can utilize the regolith for living on the surface, for shielding against radiation, as well as dust mitigation. The next slide is just a single slide that I wanted to bring forward. Again, I believe that one of the panelists will spend a little bit more time talking about Exploration Extravehicular Mobility Unit, XEMU. I just wanted to indicate that it's the first clean sheet design of the astronaut spacesuit in over 40 years. Langley's contribution in this effort is in machining, welding, inspection, and of the embedded cooling channels in the backplate. So we're using an E-beam wells to weld the backplate, and using NDE inspection technologies to inspect the cooling channels and redesign the cooling channels as needed. The last topic I'll talk about is the lightweight surface manipulator system. So if I can have the next slide, please. So this is a capability that provides for on-orbit construction. It is solving a problem that we see existing with regards to NASA as well as commercial landers, and that being that a robust approach is needed to offload and maneuver payloads in a wide range of masses, sizes, and shapes. In the state of the art, we have serial manipulators that don't scale well to heavy payloads, don't allow us to address the needs as it relates to payload mass and size, as well as of the height and size of the lander. So these heights and sizes are significantly greater for large commercial and NASA landers as compared to those in the past. So the solution that we've developed here at Langley is lightweight surface manipulator system, which is lightweight, scalable, versatile, uses long reach manipulator that combines the structural efficiency and robustness of commercial cranes with enhanced dexterity and multifunctionality of a deployable robot arm. And we've done a lot of work at Langley with regards to designing joints of the deployable units. We have used that technology to expand the capability as it relates to surface construction, used it as well to address some of the needs associated with in-space assembly. And the last chart just gives a montage of some of the technologies that are brought to bear with regards to this LSMS system and taking advantage of versatility and multifunctionality. So on the far left of the image we're talking about, and unfortunately my pointer is moving faster than I am going to talk, so hopefully you can kind of block that out. But we use the capability for inspection, site surveying, mapping, again, coupled with ND capability, then we can inspect in an autonomous fashion any vehicle, any construction that we've already done. We've also can use this capability for large scale 3D printing, particularly with regolith. And it allows us to provide for protection in terms of habitats from space radiation, as well as from dust, the deleterious effects of dust. We can use the system for assembly and regolith excavation, as well as handling. Also can be used for astronaut elevator. We can use it to support some of the science missions with deployable structures. We've also been doing some research as it relates to deployable composite beams that are lightweight and very strong, such that we can deploy these booms in autonomous fashion. And can you go back to the previous slide, please? And meet the needs of some of our science missions. And finally, we can use this LSMS system to provide for e-beam welding, again, allowing us to meet the needs as it relates to living, working, and exploring on a lunar surface. So I'll be more than happy to talk about some of the other technologies that have been developed at Langley, but this is just a small and brief summary of the capabilities that we bring to bear. Thank you.
Thank you, Jonathan. Appreciate that presentation. Our next presenter, our third panelist, is Mr. Chris Culbert. Mr. Culbert has spent more than 30 years developing technologies and systems for human spaceflight at the Johnson Space Center. He is managing the Commercial Lunar Payload Services Project at Johnson Space Center, where he is responsible for delivering NASA payloads to the moon using commercial services capabilities. Previously, he served as the chief technologist for Johnson Space Center, responsible for coordinating center strategies for technology, and also as a flight controller in the Mission Control Center, where he supported navigation analysis for more than a dozen space shuttle missions. And I'll turn it over to you, Chris.
Thanks, Jim. I'm going to, while my charts be brought up, I'll take a slightly higher level look from a technology perspective and then relate that back to some of the things we're doing on Eclipse and how that might enable the ability to demonstrate and get ready for human exploration by preparing our technology options. So next chart, if you would. I'm going to start with the chart some of you may have seen. And there's multiple versions of this, but this is at least one way of trying to capture all the ranges of technologies that need to be matured to enable human, extended human missions on the moon and eventually Mars. It starts with, basic capabilities such as automated rendezvous and docking, deep space navigation, all the kinds of things that enable you to get people and systems to the location where you want to go, progresses through things like power and power storage, deals with the entry, descent, and landing capabilities, which are quite a bit different between the Moon and Mars, but relevant to both locations. I touched briefly on life support. We have to be able to have long-term regenerable life support capability to keep humans alive without an extended resupply chain. We also need some of the lightweight structures, and Dr. Ransom touched on this a minute ago, the kinds of tools and capabilities that enable us to build larger structures in different gravitational environments are important, and the tools that enable us to do that construction work. Spacesuits are a big deal. Leanna's going to talk quite a bit about that in a few minutes, but dust in spacesuits is considerable problems. We knew that from the Apollo era. The Apollo crew members struggled to keep their suits clean and brought an enormous amount of dust back into their living environments, which is not a good thing for the short Apollo missions. We could live with that. But the crew members did talk about, scratchy throats and some respiration aspects due to the dust they brought into the environment. When we have humans living for 30 days, 60 days, 90 days on the moon, that we have to avoid bringing dust into their living environments as much as we can. Joyce talked some about rovers and the importance of mobility as a part of enabling human exploration activities, and really it's actually important to science activities as well. Viper is a good example of that, but on CLIPS we're flying small rovers of one kind or another on just about every CLIPS mission we're taking to the surface of the moon. So roving and mobility and the ability for those to operate reliably and effectively in dust environments is a critical technology. And finally, I'll get down to some of the other aspects of the longer term energy storage and production capabilities that we'll need to enable long duration missions and might be critical to enabling Mars exploration in general. So there's a wide range of technologies that cover an awful lot of different topics. You're hearing aspects of that in more detail from some of the other panelists of this mission. I won't go into a whole lot more detail here. Really what I'm trying to get across is that human exploration requires us to tackle and mature technologies in a wide range of areas. Let's go to the next chart if you would. The moon turns out to be a pretty good proving ground for many aspects of those technologies before we take them onto Mars. There are a variety of ways you could prioritize all those technologies. This is a somewhat JSC-centric view of which technologies are most important to mature, geared towards areas that have a lot of participation and support from JSC organizations. But autonomy, robotics, rendezvous and docking, mobile systems, all those kinds of infrastructure and tools that support and enable the humans to do more are important areas of investment. Life support, we've been investing nonstop in life support as a part of enabling humans to live in space for close to 20 years, continuously now. But our resupply algorithms, the processes we use to keep those life support systems operating at space station, need to be advanced even further as your supply chain gets stretched further and further away from Earth. The moon is just a few days away, so resupply of the moon is not unreasonable. Mars is many, many months away. Resupply of Mars missions isn't very practical. So we need to get our life support systems to extend both their capability and their reliability while reducing the amount of resupply and logistics they need to support them. I won't go into much into spacesuits. Those spacesuits are an important characteristic. Moving from zero-G environments to gravity environments has a number of aspects that affect spacesuit design and capability. And of course, we want spacesuits that are far more capable for our next crews that go to the moon than we had for the Apollo era. Human class entry and descent and landing is much more of an interesting discussion on Mars than in the moon, but there are still aspects of landing safely in the moon that are important. The moon is a pretty rugged environment. Your day gets real bad real fast if you land on the wrong rocks or on the edge of a crater. So the ability to find and select the right landing site, preferably autonomously, because we won't always have humans in the cockpit, is very critical. We've actually spent an enormous amount of research over the last 20 years at space station understanding how human biology reacts to living in zero-G. And we know a lot more today than we did. There are some very important aspects of enabling humans to be productive and live long-term in zero-G environments that we know a lot more about now. But we don't know much about humans living in partial gravity environments. Obviously we grew up and evolved in a 1G environment. We did not grow up in a 1/6G environment like the moon or a 1/3 G like Mars. While we expect many aspects of the human adaptation in those environments to be similar to what we normally experience in 1G, there are likely to be both some surprises and some areas where we think the different gravity environment will affect human biology, and we need to understand that and prepare and plan for that in the same way we've done in 0G. So that will be a fairly healthy area of research activity as we go along, and development of tools and techniques to enable the humans to be more productive. Almost every scenario of long-term exploration in deep space requires some utilization of resources from the local environment, providing all the oxygen, the water, fuel, other resources that humans need to be productive and effective long-term. Providing all that from Earth is enormously expensive and requires a very long supply chain. So the more we can utilize local resources, the better. So in situ resource utilization is a terminology that NASA's developed for covering all the research in those areas. It can be something as simple as looking for volatiles in permanently shadowed craters on the moon so that we can turn those volatiles into potentially oxygen or water or fuel. On Mars, it would be digging through the surface and finding ice below the surface, converting the carbon dioxide atmosphere into oxygen or potentially carbon for use in fuels and breathing. In situ resource utilization is one of the biggest keys to enabling longer duration exploration, both at the moon and at Mars. And then finally, it was mentioned multiple times by previous panelists, radiation protection is an important storyline. We are well protected by the combination of our atmosphere and the Van Allen belts on the surface of Earth. Those protections won't exist when we go to places like the moon or to Mars. There is some lesser protection from the Martian atmosphere, but not as much as the Earth atmosphere, and basically, of course, no atmosphere on the moon. And if there's no radiation, magnetic belts to provide the protection that the Van Allen belts do for Earth. So finding better tools for both managing and mitigating radiation and in understanding how that affects both human health and system performance is a key aspect of developing technologies. Next chart, please. So while NASA is interested in working and advancing those technologies in a variety of different ways, and you've heard about some very impressive ones already today, we aren't necessarily going to do this alone. There are opportunities to tap into commercial industry and enable us to utilize advances in commercial industry or from partner companies across other countries. So these areas are all ripe for advancing both terrestrial interests and space interests. And obviously one of the more important areas is finding overlapping aspects where advancing a technology both makes life better on Earth while enabling us to do more complex, more interesting missions in deep space. Where I'm focusing most of my energy these days is in the last bullet there, transportation logistics. The first big hurdle of doing anything at the moon is enabling us to get back and forth both more frequently and more cheaply. The agency has been turning towards commercial opportunities in a variety of frameworks. Commercial cargo and commercial crew get both supplies and humans to space station. And we've turned the responsibility for developing those systems and managing the infrastructure over to commercial companies, and NASA buys services from them. We're now starting to talk about extending that framework to the moon. The human lander, HLS, it will be a commercially provided lander system for taking humans to the moon. That's a little further down the road, no sooner than 2024. Prior to that, we've already engaged and built multiple contracts with companies to provide smaller scale landing services and deliver science instruments, logistics, technology demonstrations to the moon via CLPS, the Commercial Lunar Payload Services contract. That's the program or project that I manage. We have 14 companies under contract, currently 6 task orders to deliver more than 40 NASA payloads to the moon, starting as soon as late this year or early next year. So you'll start seeing smaller landers in the range of 100 kilograms of payload to the surface of the moon within less than a year. Those are kind of paving the way and helping develop the commercial infrastructure that will enable NASA to tap into a broader suite of services as our exploration interests grow and our ability to do things on the moon expands. It's hard to emphasize how important it will be to have the ability to fly to the moon multiple times a year. we're currently planning at least 2 CLPS delivery missions per year to the moon, starting, like I said, by the end of this year or early next calendar year. And we have sufficient budget to sustain that long term. So the ability to go to the moon twice a year, multiple times, means that we don't have to get every technology demonstration exactly right. And every science instrument has to be perfectly developed. We have the opportunity to build smaller scale instruments on a potentially cheaper budget, send them to the moon, gather data from them, and then fly again within a year or two to advance the capability beyond what we did in the first mission. We can also use that capability to pre-position logistics for human missions. So we could potentially provide water that the humans will already be on the surface of the moon, ready for them before they bring down to the surface. For Mars missions and even for lunar missions, we could in place ISRU plants, the ability to generate fuel or potentially water or oxygen from the local environment, have those working robotically prior to the humans arriving so that we don't have to take all the fuel, water, or oxygen humans will need to do their business once they're there. So the CLPS and tools like that are enabling a new way of NASA getting that work done. What we've seen in the early stages of CLPS, we haven't landed on the moon yet, so that big stuff still needs to be demonstrated. But the early stages, we're already seeing significant payback in terms of cost. The cost of CLPS missions are a fraction of what a typical NASA mission would cost. We've seen cost as low as $47 million for taking about 40 to 50 kilograms to the surface of the moon. That's close to an order of magnitude cheaper than anything NASA could even consider providing. So the commercial enterprise is already lowering the cost. And we hope to also get some innovation out of the commercial sector. They'll bring new approaches towards flying and competing missions. They'll bring new technology to the table. They'll bring new capabilities to the table. We hope to be able to tap into that to enable a much broader swath of NASA capabilities and missions down the road. Next chart, please. So I'll just mention these. I actually hit many of these already, but I'll mention in passing. There are a variety of key drivers for deep space exploration. All of these tie into being further away from Earth. I've mentioned a lot of these already: logistics, supply, long mission times, crews won't always be available. So all of these tie into the investments and the needs for technology development and how we pull those together. Next chart, please. I think I'm going to wrap up here. The key message is that the way we've done missions in the past isn't necessarily how we need to be looking at doing lunar missions and Mars missions in the future. Technology is critical to enabling us to do these things in more innovative ways. Investing and encouraging the kinds of game-changing technologies that the agencies are investing is critical, and utilizing new algorithms, new approaches, new methodologies like commercial services, I think are a big part of enabling us to get to where we want to go long term. So I'll wrap it up there.
Thank you, Chris. Thank you very much for that overview. Appreciate it. Our fourth panelist is Ms. Leanna Rodriguez. Ms. Rodriguez is the project manager of the Exploration Extravehicle Mobility Project, which is developing the spacesuit for Artemis 3 lunar missions. She has worked as a systems engineer and project manager on a variety of projects during her career, including the Lunar Mars Concept Studies, X-38 Crew Return Vehicle, Orion, and EVA suit ports. In 2014, she received the NASA Silver Achievement Medal for exemplary leadership in the area of advanced spacesuit development. And I will hand it over to Ms. Rodriguez.
Hello, thank you very much. I hope you can all hear me okay. I had a little technology issue here joining. I'll jump right in because I think we're running, we don't have too many time for questions. So you heard a lot of panelists mention spacesuit development as a key technology for surface exploration. So that's what I'm here to tell you about. Next slide, please. Just a little background. It was actually mentioned that the spacesuits that everyone is used to seeing from NASA were actually designed more than 40 years ago. So the Apollo spacesuits were the last time that we had a planetary suit actually operating during the Apollo missions. But ever since then, the suit everyone's familiar with is called the EMU, or Extravehicular Mobility Unit. And it is optimized for use in microgravity environments. So as we look forward to surface exploration, we have a couple of different, quite a few new challenges, but one of which is just adapting to the environment of the surface, starting from where we've been used to operating for a lot of years here in microgravity. At the same time, we want to make sure that the suit that we develop is in a way backward compatible, if you want to call it that, to where we could use that same spacesuit in at space station if needed, or other low Earth orbit destinations. So next slide. So the spacesuit of the future will have to have a lot of more capability than we have had to date. Some major points are, it needs to fit a much larger population of crew members, both men and women. The original suit was designed before women were part of the crew. And it requires a lot of different size elements to fit different crew members. We need to be able to support, as I mentioned, missions in different environments: lunar surface, cislunar space, and low Earth orbit. We want to reduce the possibility of the suit injuring the crew member. It is a very intensive thing to use the current spacesuit in any operations. It needs to be extremely reliable, including new and rugged technologies and a lot of redundancy. We need to require less crew time to maintain and prepare for EVAs. And we need to also support the fact that these missions won't be as frequent. So we may have to leave our suit hardware at our destination for longer periods of time between uses, and make sure that quiescent stowage period doesn't cause any detrimental effects to the operation of the suit. The suit needs to have a modular architecture, and we're designing it with as many standardized interfaces as possible to make replacement of components easier, and for whether it's for repairs or for upgrades. And then finally, we need to try to minimize the entire system consumable. So that's beyond the spacesuit, right, for the whole mission. And the spacesuit plays a part in that by incorporating technologies that don't require resupply of certain items throughout the mission. Okay, next slide. With those items in mind, I'm going to dive into a little more information about the design of the XEMU. These images here are one of our early prototypes for the XEMU, with one of our spacesuit engineers there demonstrating. In particular, that middle photo there shows you some of the mobility characteristics of this suit. That is one of the big advances, is the mobility and fit of the suit for allowing crew members to operate as naturally as possible when they're serving as geologists on the lunar surface, for example. The spacesuit is made up of 3 subsystems. The pressure garment subsystem is the suit part that is worn. The portable life support, or PLIS, is the backpack, which contains most of the life support equipment. And then the Informatics subsystem, which is designed to promote crew efficiency and autonomy. Next slide. Diving into the pressure garment a little, I mentioned before, one of the big changes is working in a gravity field, again, on the lunar surface, means that we need to be able to walk in the suit. So you've seen images, video from Apollo of the crew members hopping around the surface. You also saw them fall down quite a lot. And although that suit was a marvel in technology when it was built, we can do better now with how the suit moves with a person and allows them to operate more naturally. So they should not be falling down as much, and they will be able to walk a lot more naturally. And that is courtesy of the lower torso assembly, which has bearings at the hip and at the ankle, and a flexible knee joint to allow them to walk more naturally. This suit will also need rugged boots for working on the lunar surface terrain. So they will be a lot more like a hiking boot. Another big difference from the current EMU to the XEMU is the way that the crew member dons and doffs the suit. So rather than putting it on like a shirt and pants, the XEMU has a hatch in the back which you can see in the middle photo there, or middle CAD model there. And the crew member basically climbs into the suit through that opening, a little bit like getting into their spacecraft, because this is a little mini spacecraft. One of the reasons for that design is it allows for the upper torso to have better placement of the shoulders. So these shoulders that we're building are highly mobile shoulders. They fit better, they fit more naturally in the places where they need to go on the human body to allow for the natural range of motion of the shoulders. In the current suit, you cannot really reach across your body with your arms, you cannot reach over your head. With these shoulders and this hut configuration, you are able to do those types of motions. The helmet for this suit is also an elongated shape, which allows for greater visibility in the downward direction, which also comes in handy again for surface operations, looking at the ground, basically. I should mention, let's see, this suit also uses an integrated communication system. Basically, that just means they're not wearing anything on their head, no headphones. Their speakers and their microphones are integrated into the volume of the suit, which does pose some challenges, definitely in the audio realm. And then finally, the environmental protection garment is the outer layers of the suit, which are providing the direct protection from the environment. We put in thermal extremes. You heard a lot about dust earlier. That's a big consideration, and other potential hazards from the environment. Next slide. Okay, for the portable life support system capabilities, basically your life support has to provide you oxygen to breathe, pressurization for the suit to provide pressure inside the cabin or inside your suit, and carbon dioxide removal, and then thermal control. So listed on this chart, I won't read every one of them, but are some of the technologies. And some of the key newer ones are right in the center of the plus package there is the rapid cycle amine, which is a CO2 removal system, which is regenerable by vacuum. So it basically has two beds. One bed collects CO2 from the environment of the suit, while the other bed is being rejected outward. So that is a key new technology. The other key new technology here is the heat rejection. It's called the spacesuit water membrane evaporator. And we actually have a flight experiment on space station right now with this part of the spacesuit. It's called the SURFy flight experiment. You can look that up. Okay, next slide. The life support system actually has components that are not located in the backpack. So the hatch, the inside of the hatch of the suit, of the pressure garment, also has some life support components. That is where we have our feed water supply for the thermal control, and also our trace contaminant. And the trace contaminant cartridge is placed there because of easy access. That is one element that currently would need to be replaced after a certain amount of use. The other element that controls the life support system is the display and control unit. That triangular shaped item here on the screen mounts to the front chest of the suit. And that is the way that the astronaut can interact with the life support elements with controls and information there. Okay, next slide. And then finally, the informatics. Informatics is focused on crew efficiency and autonomy. For the early designs of the suit, the focus for that is on the lights, providing basically LED lighting now to illuminate the work area. The work area is different and larger than it is during microgravity EVAs, where everything is centered right in front of the chest of the person. On the lunar surface, your work environment is bigger than that. And then also the camera is HD video and stills, and there is an avionics box basically with Wi-Fi antennas that can collect the suit data and the videos and transmit those back to the vehicles. And that was a really brief overview, but that's what I wanted to do, to just introduce to you the different areas. Each of these capabilities and functions of the suit have their own individual technology development and challenges that are ongoing. But I hope you enjoyed that. Thank you.
Thanks, Leanna. That was a really nice overview of the new suit. Thank you very much. And I guess now we have a few questions. We don't have too much time left, but we have a few questions. And Jim, I think you're going to do those.
Sure. Yeah, we sure do have some questions. So one question came in about, if we're talking about our theme of convergence, any lessons, and I'm not sure who this might be for, but with dust, any lessons learned from our space exploration that are applicable in dust mitigation that are applicable here on Earth in terrestrial applications, vehicles. One example comes to mind in my mind anyway is an airliner flying through volcanic ash. Is any of that applicable? Anybody jump in who might? Joyce, you unmuted. You got something?
Yeah, I guess what I can say is, some of these things like how we deal with at least the rugged terrain elements of, loose soil and dust. There are a lot of applications in convergence with the rover systems and the mobility. So, that is one area where we might be able to say, okay, here's some things that we've done to develop these for these operating in dusty, difficult terrains, and those are some things that we can kind of bring back to Earth. Even the mechanisms like for the excavation, things that we can do with, say, drilling, for example. That's more on the rocky side than the dusty side, but certainly, all of those things. And I'm thinking too, just even, on the fly here, things that might have to happen, operations in desert environments where there's a lot of risk of getting those very abrasive particles into mechanisms. So the things that we learn could very likely influence designs for mechanical systems that are more rugged and reliable for those environments.
Gotcha. Good. Thanks.
And just to chime in on that as well, Jim, I believe that the technology that has been developed, say, for aerospace applications or aeronautics applications with regards to adhesion, play a role in the materials that we're developing for dust adhesion or to mitigate dust adhesion. So some of the adhesion technology as relates to bugs and or icing is the same type of technology that or certainly the expertise that's brought to bear is the same type of expertise that's brought to bear for dust mitigation.
I suppose spraying a solar panel with Teflon isn't an answer, right? So that won't work. So related to dust, how important is it for us to get good sample returns to understand the true characteristics of what we're going to experience when we get there? We can only simulate so much, right? Chris, or Jim?
Well, clearly it's important, right? Though it's also, so more awareness of lunar materials would be very valuable in that context, particularly in scale, so, larger quantities, so you could test them in some interesting ways. But don't forget, their behavior in terrestrial environments won't necessarily be the same as behavior in vacuum on the moon. So there's some limitations to how far you can take that. Sample return is a ways off, but it is on the horizon for CLIPS. We're really just waiting for our vendor pool to tell us they're ready to take on those kinds of missions. That's going to be a fairly challenging mission, though.
Gotcha. Good. I have time for one more quick lightning round question. I'm going to go around the table. Everybody has 10 seconds to answer, and I'll start with you, Leanna. What's keeping you up at night, aside from storms in Houston? Working to unmute. She's working to unmute.
Sorry, couldn't get my thing to cooperate there. Oh God, what keeps me up at night? I think that we want to solve all the problems right now. We want to solve them all. We want to do the absolute best we can initially, but having to pick and choose a little bit what areas are the most critical to have early on in the first few missions, and then allowing for some of those other things to mature more with time. So I think that's one thing.
Gotcha. Joyce?
Yeah, and I think we already said it. It's dust and just kind of how it can bog down these, these mechanical systems. Just wanting to see that be successful in coming up with the technologies that are going to make that possible.
Chris?
So, from my perspective, we're making a lot of progress with these commercial companies, but until one of them actually lands on the moon, I can't, we can't fulfill a lot of that potential promise. So that first landing on the moon is going to be critically important to us.
Gotcha. Jonathan?
Fully integrated multifunctional systems, ones that can protect against dust, space radiation, impingement from micrometeor debris or dust, all key issues.
Gotcha. And Jim, I'll let you answer, and then you can conclude. So unmute Jim.
Yeah, I think radiation is probably going to be one of the biggest factors there, from the galactic and cosmic radiation. We were lucky with Apollo, but we're going to be there a longer time, and as we go to Mars, it's even going to be a longer time. So I think radiation is one of the key technologies that I think keeps us up.
Gotcha. Well, hey, panel, thank you so much, everybody. That was awesome. And as always, an hour isn't enough. I wish we could have gone longer because we could keep going, because I have a lot of questions for you guys, but maybe we'll come back to it and do some chats or something like that online. But thank you very much to our panel. We really appreciate it. We're now going to take a lunch break. So we'll take a 30-minute break, 28 minutes, and we'll come back at 2 p.m. For a very powerful session. Thanks, everybody, and we'll see you then.